In previous videos, we've talked about the biosynthesis of fatty acids and pheromones. In this video, we're going to look at the way that bacteria make these molecules we call macrolides. Now, these macrolides are very interesting molecules because the bacteria make them as antibiotics. Because if you're a bacteria, your greatest enemy is another bacteria, and you do whatever you can to fight them off. So erythromycin is this particular molecule right here, which is a widely used antibiotic, and you see it's compared to penicillin here, and is used for people who have an allergy to penicillins. Now this is erythromycin A. It is not completely a product of the polyketide synthesis, but it's derived from this molecule, which is. And you can see what the differences are. There's two oxidations here. There's two extra hydroxyl groups that show up here. These are post after the PKS enzymes are done. Other enzymes come along and do those two oxidations, and then these two sugar-like molecules are attached. So, but we're concerned with this basic core molecule right here. How is this thing made using the polyketide machinery? So let's take a closer look at it. What's the primer for the biosynthesis? Now, how in the world would you figure this out? Well, what you do is you look around this molecule and you see it's a lactone. And this lactone, of course, is assembled, is this ester linkage here. You'd have a carboxylic acid on one end of the macrocycle, and you would have an alcohol on the other end. Well, this is the key to figuring out what's going on, is because the carboxylic acid is the final end, and the alcohol is going to be the beginning. And think about this, alcohol would have come from a carbonyl there. Now, if it was just from regular acetyl coenzyme A that this thing whole started off, there would be a methyl group here and not an ethyl group. So the starting material must have been B, the propionic acid derivative, because that's the way you get an ethyl group at the start. So now we're going to go around the circle all this way. Now, so how many malonate extenders were used? Okay. What malonate extenders were used? Well, we have a choice here between methyl and ethyl. So if we look around here, what do we find? Well, we have an ethyl group right here. Does that mean an ethyl extender was used? Well, no, that was the starting, that's the primer. So let's look around. Well, there's a methyl. There's 1, 2, 3. There's another methyl. 4 methyls. 5 methyls. 6 methyls. Did I count right? Let me go around here again. There's 1 there, 2 there, 3, 4, 5, 6. 6 methyls. So it looks like 6 methyls were used, and there were no ethyls. Okay. So that is our basic scheme that we're going to be looking for. Now, this is the way this thing is drawn out. Look at all this stuff up here. What does this all mean? Well, there are 3 main modules. They labeled on the top down here, and then there's submodules within those modules. This is basically just talking about how the various enzymes are assembled together in terms of associations. And look at these abbreviations. These are all the standard abbreviations that we talked about when we were doing the fatty acids, and like the KR, for example, is ketone reduction, and you just go through each of these and it's telling you what's happening. But basically, if you just watch this thing grow, here we have our ethyl group to start with. Then we're just going to add our various units. So here we add a methyl malonate. And that carbonyl gets reduced. We add another methyl malonate. We add another methyl malonate. We add another methyl malonate. We add another one. We have another one. And so each of these fundamental steps, and what we end up with down here, we could look at our methyls. 1, 2, 3, 4, 5, 6 methyls. There's our ethyl out here. We've had some ketones haven't been touched. Some ketones were reduced. The ketone right here was not only reduced, it was dehydrated and hydrogenated. So you can see what steps were used at which points along this thing. So this is just like a fatty acid synthesis, except all these steps were various steps were skipped. And you can see how complex this is. Look at all this enzyme. 1, 2, 3, 4. I don't even want to count them. You can count them. How many different enzymes were used for this just to make this crazy molecule. So these little bacteria are really busy. Okay, so then since we have this linear molecule, of course, what we have to do then is a cyclization. So this, again, this is all enzyme driven. So this lactone is formed by this alcohol here cycling around into the ester, kicking out the sulfur to form the cyclic lactone, and then you do these 2 extra oxidations and add your sugar-like molecules. So that's pretty wild. Okay, let's talk about another one. This is another important antibiotic. This is one of these things that they feed cattle. So when you talk about whether you have antibiotics being used in your food chain, this is one of the culprits. This is one of the antibiotics they put in a cattle feed and to as a preventative, and lots of people don't like this at all. And what this particular does, and well, like a lot of these antibiotics, what it does, it messes up ion transport. And so this thing acts as a chelate. All those inward pointing oxygens wrap around and grab various metal ions, and it can transport these metal ions across cell membranes. And you can imagine it can that can really mess up a bacteria if you screw up its metal balance. So how in the world would you make something like this in a biosynthetic pathway? It looks extraordinarily complicated, and look at all those rings. This is crazy. So anyway, it turns out this is the known precursor before you have all these rings. And so let's figure out what's in this thing. So how many? Where this particular one uses malonic acid. It uses the regular malonate, the methylmalonate, and the ethylmalonate. So how many ethyls are there? Well, let's look. There's one ethyl right there. Okay, so there's one ethyl in this whole molecule. How many methyls? Well, let's count. There's 1, 2, 3. I skipped that. So there's 4. There's the ethyl. 5, 6, 7. Is 7 a choice? Good. I think it's 7. This one here wouldn't count because that would be, this is going to be the primer. All right, we're going to end with the dicarboxylic acid over here. So 1, 2, 3, 4, 5, 6, looks like 7. And then how many malonates? Now, this is actually the harder one to find because you got to look where things are missing. So go look at the every other one position. So methyl, 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 nothing. There's a nothing. There's another nothing. There's a nothing. There's an ethyl. There's a nothing. So how many nothings were there? I didn't count. There was 1 here. There was 2, 3, 4, 5. I think it's 5. So there's 5 malonates. So that's quite a collection of compounds. So again, this thing is put together by all this crazy assembly of steps. You can see there's some ketones, there's alcohols, there's double bonds, there's regions which are pure hydrocarbon. So you can tell you there's quite a variety of reactions are used on all this. Well, this thing will naturally form a hemiacetal right there. So this is the species which readily forms. And so where does this all come from? Well, how does it form those final rings? Well, it turns out you need more oxygen. And so there's an iron enzyme which comes down and forms epoxides from these various double bonds. So you form this scheme of epoxides, and then in a very fun thing, you attack that with base, and you just go around and you open those epoxides and you form bigger rings. Can you draw that out? It looks quite exciting, and you get Monensin drawn out like that. So this shows you how wild these these things can get. So you have a couple other modifications here. There's a methyl group added there. There's an oxidation over there. But that's so Monensin is pretty much a polyketide without a whole lot of extra stuff. Okay, so this is Rapamycin, which is a macrolide which is used to coat coronary stents, and it's quite a molecule. Look at this. This is about as complicated as we want to think about. And where does it come from? Well, it comes from these particular bacteria, where all these things tend to come from. The Streptomyces bacteria. And where do the Streptomyces bacteria come from? Well, it comes from Easter Island. So people get dirt samples from Easter Island. It comes from dirt. They isolate the bacteria from the dirt, and then they isolate the rapamycin from the bacteria. So look at this crazy thing. So can we figure out a little bit about how this was put together? Well, this was all worked out about 10 years ago, so let's look at this a little bit. So look at these. There's a couple red methyls here. I get they're the methyl ethers. Where do these come from? And well, of course they come from SAM. Remember, the very first the biosynthetic pathway we talked about was methylation of SAM. And so, of course, if you have alcohols, they can be turned into methyl esters or methyl ethers using good old SAM. What about the other methyl groups? There's various other methyl groups around here, and of course these other methyl groups are from the methylmalonate extenders in the basic pathway. So how many of these? Oh my goodness, we've got to go looking here. So let's go along very systematic. Who wrote this question? There's one methyl there. There's two. There's three. There's four. There's five. There's six. There's seven. There's something weird up here, but it looks like 7 methyls. So it must be D. So it must be 7 other methyl groups. Okay, look at this. Okay, this is the enzymatic system up here. Look how complicated this is. 3 main modules, and then all these smaller modules. There's 14 smaller ones, and you can just simply see this thing growing out. Now, this is what's the fun part. It has a very unusual primer. It's got this ring here, which is the thioester that it starts with. So this is the primer, okay? And then as it just goes along, it's going to simply add these various it's going to add either methylmalonates or simple malonates, and it's either doing it's doing reductions or not doing the reductions, doing dehydrations or not, as you go along this whole thing until you get to this final molecule right here, okay? And now this molecule does something a little bit differently, because when you have there's further modification of this by adding this amino acid, which has been derived from lysine. So this amino acid actually adds into this thing, and it gets incorporated into the ring down here as well. And so this is what comes off the system. It's not just a simple lactone, because of the presence of this amino acid, which actually ends up forming, it's actually now a lactam, because it's a cyclic amide, not a cyclic ester. And so after the PKS system is done, there's some further modification of these methoxy groups, and there's an extra oxidation over here on this particular carbon right there, and so that's the synthesis of rapamycin, which I think is really very, very remarkable and tells you how complicated this all can get. But look at that. Evolution has put together this gigantic assembly of enzymes just to make this one molecule. So you'd better be good, because there's lots of energy has gone in to putting this all together. So that's a quick look at macrolides, and I hope you find them as remarkable as I do.